So he's an assistant professor in the School of Mechanical and Aerospace Engineering at Oklahoma State University. He received his PhD in 2007 from the Department of Mechanical Engineering at the University of Kentucky. His doctoral research was focused on developing plasma actuators for flow control applications in micro-aerial vehicles. He worked at the Carolina Center for Interdisciplinary Applied Mathematics at the University of North Carolina, Chapel Hill, as a postdoctoral fellow, investigating fluid structure interaction phenomena occurring in biological systems, including vortex formation in the developing vertebrate embryonic heart. Following UNC, he pursued research in cardiovascular fluid mechanics at Georgia Tech, biomedical engineering. There, he simultaneously worked as the primary engineer in a collaborative research project between Georgia Tech and Children's Healthcare of Atlanta to design and develop a renal renal dialysis device for use in infants and children. And currently, he directs the Applied Fluid Mechanics Lab at Oklahoma State University, conducting research in the areas of heart failure, flying and swimming of tiny insects, crustacean swimming, and pore water pumping by upside-down jellyfish. So today, I don't think he's going to be talking about jellyfish or insects today, but he's going to focus on cardiovascular health.
I'll put a little thing in the front. Thank you. So I'm really glad that some of you guys showed up, either by choice or because you have to satisfy the seminar hours, but I'm glad you're here. So what I'm going to try and do today is just to give you a flavor for the type of approach that I'm using to understand some of the blood flow dynamics in your heart. And most of this is done with experimental methods that are pretty common to fluid mechanics all around. Okay. So the main focus of my lab, in a way to try to connect that all these different projects, is essentially things that are creepy crawly. They move in fluids, and they create all these other effects because of it. And so what I'm really interested in looking at some sort of interaction between morphology, so in other words, geometry and structure. How does it interact with mechanisms in which things move, whether it's for pumping blood in case of your heart, whether it's for moving in air or water, whether it's a tiny bug, for example, or feeding, catching prey under the ocean. In other words, is there physical design principles that govern that, right? So the idea is to use experimentation with models, organisms, and so forth to try and understand how the mechanism is engineered. And so the idea is that down the line, can we actually use this to develop devices, whether it's biomedical devices, heart valves, artificial pumps, so on and so forth, to be able to benefit engineering applications in medicine, for example. Okay. And the common sort of theme is that Reynolds number is in the lower end, where I'm looking at from anywhere from 0.01 order of magnitude to about 1,000, so several orders of jump. So here's an example of how Reynolds number can actually change the developing heart. So as the heart develops, in this case, this is a mouse heart from an SEM image. And so as the heart actually develops and forms these multiple chambers, atrium and ventricle, into the four-chambered heart that's inside our body, there's a whole series of morphological changes. With the morphological changes, there's actually a change in the blood flow patterns. There's vortices being created, and vortices, high shear regions present in the blood flow tract. And so these can actually influence the development itself. Okay? So that's a very interesting way to think about it. The developing embryonic heart is actually, the blood flow is not just helping it to actually supply nutrients, but it's actually, more importantly, it's helping to develop the heart itself. And then in case of external flows, these are internal flows. In case of external flows, I look at organisms where there's a large amount of undulation, so there's a structural motion that's actually quite drastic and noticeable, and there's flexibility, there's all these little microscopic branches and so forth. And as you notice, as the dye is being injected, this is sand, these jellies actually pulse and they drive the jet upwards, and as a result, they're pumping stuff from the sand, they're taking it up, and they're creating some sort of diffusion and mixing in the water column, right? So what's really cool about this is that, to me as a fluid dynamicist by training, This is challenging because there's a whole lot of hierarchical structures here. There's the big bell, there's the actual structure that's like a blocking mechanism, there's all these tiny little branches, and how do these interact in isolation, in collective organization to be able to create this net effect, right? And the other thing that I'm looking at is how these tiny little insects, so this insect here is in the scale of, so that's a, by the way, just to give you a scale, that's a matchstick tip, okay? So that's an order of about 1/4 millimeter, okay? And they flap at about 200 times a second, the wing beat frequency. This was imaged with multiple high-speed cameras at 4,000 frames a second, okay? And there's not a whole lot of footage, so I'll use this shamelessly over and over in many talks. Because it's hard to get. But what's cool to me is that studying these can inform us, for example, how do I miniaturize something that flies? How do I make a device that filters water, that uses some sort of unsteady mechanism? Typically, you think of filters, you just think about something that you fit into your faucet or something that you have that's just kind of sitting there. It's not doing anything actively, right? One of the applications for this could be when I was doing my dialysis device, I had to use filters that basically make urine from blood, that basically are a set of straws that they use in us for little kids, and that wasn't efficient. Okay, so the idea is that can we make biomedical devices more adaptive to the scales by using ideas from nature, nature's designs, and actually applying it for engineering. So kind of a very sharp segue into cardiovascular flows, because that's going to be the focus of today's talk. Why study cardiovascular flows? Well, that's clearly society importance. Just in the US this year, there's more than 5 million people living with heart failure. And this is not just a singular sort of condition. It's actually multiple roads that take you there. So it could be a result of valve incompetency, valve defects. It could be tissue. Your heart tissue could be stiffer. There's maybe cells that are dying in it. It could also be part of the electrical circuit in your heart. So it could be conduction related. So there's many roads, but the outcome is that the patient's quality of life is impaired. They're not able to walk down the set of stairs like you and I could so easily. And so there's definitely applications to seeing maybe we can engineer new devices, maybe try and improve the diagnosis that cardiologists use, maybe by adding some more mathematics into understanding the blood flow. Right? And so what happens in many conditions, for example, this is a congenital heart defect that's present in about 1 in 500 people. Whether you know it or not, it's really a game of chance. A lot of people might have somebody that they know that died as a teenager, just a very active athlete, sudden cardiac death. Most of the time it's because of this, where the heart muscle just starts thickening. And what happens is the flow inside here and here, you can kind of physically appreciate visually, but it's not going to be the same. It's not going to look the same. Can we actually use this to diagnose the heart structure itself so that we can maybe improve our therapeutic delivery earlier, for example? These are the questions that we're interested in. And to me, again, circling back to the fluid mechanics question, the heart is nothing but a pump, right? So that's really the heart of it. But so how is the pumping affected when you have structural diseases, right? Structural heart diseases can lead to heart failure. How can we improve cardiology as we know it? Multiple different approaches exist. So if you talk to a cardiologist, a practicing clinician, most of the times they look into the realm of in vivo studies. So that can include clinical studies. So they have some sort of a protocol. They recruit people with some sort of an inclusion criteria. They do a whole lot of statistics. They try and recover statistical correlations. Okay? Does it really give you an idea of the mechanism behind it? Probably, probably not, more so. The other option is to go to animal models, which if you go talk to the people in VetMed here, they'll probably be doing this as we speak. And so, again, these two are stifled and challenged by the fact that you cannot choose your disease and control it. Right? To me, as an engineer, I'd like to be able to control. I want to have knobs in everything that I do so I can move those knobs, make the system do what I want. Right? It's a more deliberate type of investigation that I like. So the next approach, which is more intuitive and common to engineers, is physical modeling. In this case, you try to make something that's not real, but it's artificial, but you try and put something similar to the real system in there. So maybe you move it the same way, maybe you have similar materials that you use, so on and so forth. And there's some sort of guiding data that helps you to design it. So maybe it's imaging obtained from patients, maybe it's imaging obtained from animals, but you use that to design your models. And then the best part about it is, like what I said, you can actually, given a carefully designed physical model setup, you can actually control different variables. You can investigate more of a causative, here's the cause, is there an effect? One by one, and try and isolate it. There's a much more controllability of it. Down the line, does physical modeling really help in terms of a clinician trying to do a surgery tomorrow? Is there, what would he or she need? What would be ideal is to maybe just to put it in a computer model, right? Take the MRI data or CT data or ultrasound data, put it in a computer model. It takes its time, spits out the outcomes, and then you make a good judgment on it, right? Given that the computational models force some sort of mathematics into the problem, into a biological problem, they also should be, goes without saying, should be designed based on some sort of guiding live imaging data. And they should also be able to accommodate the complex interactions. Physical models maybe can skip some of that in the sake of trying to get to certain variables. Computational models, before they can go and feed into patient therapies, we need to be able to accommodate a whole lot more. In other words, we actually need validation of that. So physical modeling can actually serve the purpose of providing validation data as well to computational models. So there's a back and forth crosstalk in that physical models can provide data to validate computational models, and computational models can in turn say, look, I really need more complexity in something, can you do more experiments and give me more data? So there's a healthy exchange of back and forth interactions that help to develop a more solid, validated, clinically relevant computational model that hopefully somebody can use it in the bench, in the bedside. Just to kind of quickly, for those who are not looking at fluid dynamics, I just put this out there. But the main idea, what I'm trying to drive here is that these are the governing, non-dimensional governing equations of fluid flow, Navier-Stokes equations. And so the general idea, if I just look at one dimension, the momentum equation, you get this Reynolds number factor from it, and it's essentially nothing but ratio of inertial and viscous forces. So matching Reynolds number between two systems essentially ensures that the forces experienced by one system and another system are similar. Okay, so that gives you some a roadmap to building models that hopefully will be close enough to represent the actual organismal life system. Changes in Reynolds number, do they matter? Here's one of my favorite fluid dynamicists, G.I. Taylor. He did this really cool video of a tiny little propelling robot, the battery. So this is Reynolds number that's a very high order of magnitude. The fluid isn't viscous, like water maybe. So now I'm going to play this, and bam, it just propels itself, no problem, right? What do you think will happen here? This is corn syrup. So do you think it'll move? Now, let's just say it doesn't move, they get a piece of candy from there, right? So it's not going to move. Okay, that's a pretty drastic difference between the two. So changes in Reynolds number actually do matter. In case of, for example, internal flows, they can change your behavior from high shear, vortices, and stuff like that to more sort of parabolic profile and so forth. Okay, so changes in Reynolds number occur because of development, because an organism is growing, heart is growing from small to big. It can also occur because of changes due to disease, because some heart muscles contracted, maybe the length scale is smaller, so on. So changes in Reynolds number do matter. And what's interesting, for those who want to make their career, there's a bunch of graduate students here in studying fluid mechanics, in physiology. There's a lot of problems out there. Okay, this is intentionally to advertise and market my area of interest. So if you look at this, if you just look at a heart alone, embryonic heart starts over here, this is a log scale, and goes all the way there. And there's all these stages in between. If you take a look at your kidneys, the glomerulus is over here, the nephron's over there, right? Many organs in your body, right? operate across a varying range of Reynolds numbers. So what does that mean is that at every single little jump that you're making, the fluid mechanics can be quite different. Okay? And that's kind of the take-home message, is that how do we study this, and how do we use that to inform healthcare, for example? That's kind of the big picture. In terms of developing physical models, I just wanted to make a couple of notes. So typically what we're doing in terms of dynamic matching between one system to another, whether it's the real organism to the model, is that you're trying to match the Reynolds numbers, so the forces acting, the ratios will be the same. The usefulness has been noted particularly many times, and the usefulness is that you can actually control different variables in an isolated sense, but many times mechanical measurements may not be possible to acquire in vivo. So if you wanted to measure the stiffness, material property of the myocardium in a developing embryonic heart, it's going to be really, really difficult. The size scales are challenging, the motion's pretty wild. How are you going to put a probe in there? And B, do you even have a probe that can do this, right? So a lot of times you're challenged by the fact that there isn't an instrument that will give you the answer you need. Then does the answer mean, well, to avoid the problem? Maybe not. The problem is still important. Can we think of alternative approaches based on physical modeling or computational modeling to get to the understanding what's important? And it's possibly more expensive. Depending on the type of in vivo model you're using, it can be a lot less expensive. So it's one way to get your science kind of started on the right, put it on a footing, and then hopefully you can do more in the way of approaches, modeling, and live experiments also. The important thing to note is that these models, physical models, don't necessarily give you the truth. They give you something close to the truth, but you have to validate this with measurements wherever possible. Okay? If it's not possible, then maybe you're challenged by that. But if it is possible, you need to be able to validate it and say that, look, my model is able to be matching the physiological conditions and so forth. Okay? So today what I'm going to try and include in the talk is the development of an MRI-compatible left heart phantom, left heart simulator. And then I want to show a couple of applications of this facility. One is a validation of cardiovascular magnetic resonance-based reconstruction of the left heart, left ventricle volume. And the other one is looking at possible way to diagnose stiffening of your heart in a particular type of heart failure. Okay? So the first thing I'm going to start is just development of the facility. So this was in collaboration with my former postdoc advisor and another collaborator from Emory University Radiology, who is an expert in MRI, so he was able to help us with that. So the motivation of this is that, again, a lot of in vitro models exist. So what I'm showing here is not unique to what I've done. There's plenty of people that do the same thing. So this is not the world's first facility or something like that. What's typically a problem with a lot of these is that they do a good job in giving you really good data right here in the bench. What does it mean when it goes to a cardiologist's tools and equipment? Not much, because a lot of times what might happen is that your methods could give you data at a very high resolution. Maybe in time, you've got spectacular high-speed data that can give you very slow motion and stuff like that, but the cardiologist doesn't have access to that. Because, for example, a patient doesn't want to be stuck in a claustrophobic MRI bore for a long time just because you want high-resolution data. Not practical. Okay? So, but does that mean that having such models are not important? Probably not, because to translate something that an MRI machine can measure, for example, you need to ask the question, how accurate is this? Is this truly what the metric is supposed to mean? So in other words, can I have a comparable measurement from another technique to sort of juxtapose, put side by side with, and then see whether they match up? It's a very simple engineering question. You get a new type of measurement characteristic, an index from one measurement technique. You ask, is this really it? Is this the true value? And so how do you test it? You look at another method that will give you something similar, that's hopefully higher in resolution, and then you put them side by side, and then you say, look, it's very close by X%, right? And the other thing is that a lot of times, in order to predict, or not predict, but to calculate something from imaging data, a lot of times the radiology people and the clinician, the cardiology folks don't know what type of resolution they need. Okay, a lot of times, obviously, it's kind of a practice. So they say, look, we're going to do this many slices of the MRI of the heart, at this many images per cycle, and so forth. But it's based on practice. It's not necessarily based on any sense of accuracy. Okay? If we are going to move to trying to get to imaging-based modeling, so I can predict therapy's outcomes beforehand, then we need to have validation of those. And so the phantom models can actually provide a link between the bench and the bedside in terms of being able to provide data from multiple methods, and you can test the validate how accurate it is from the medical imaging side. You can also tell how accurate, if you want to improve the accuracy, this is how much resolution you need on the scan. Okay. For example, this situation is pretty serious. So this is an idealized cardiovascular device that the FDA gave to a bunch of labs around the country, research labs like many of the ones in campus here, and what they wanted to do is to simulate flow going through this. The main thing that you'll notice is the geometry is changing, there's a contraction, there's an expansion, there's some sharp corners, all of that. Surprisingly, the computational models presented quite a bit of discrepancy with lab measurements. Okay, they didn't match, especially when it came to shear stress, the walls, and so forth. And so there's basically the conclusion of this study is that we need more rigorous validation before I can use a computational model to tell whether a patient's going to succeed or not from a therapy. Right? A model is just that. It needs to have some validation. Okay? So in terms of the left heart, what we started out doing was to take volunteer data. So we put innocent undergrads and graduate students like yourself, and postdocs like me hungry for papers. We'll entice them with the possibility of getting a free heart scan. And we put them in the MRI machine and we get all these medical data. So we had a repository of this at Georgia Tech, where I was at the time. So what we started doing was segmenting the endocardial, the innermost tissue, that border, and fitting ellipses around it. And then using SolidWorks, you can actually try and fit these in a concentric manner and generate something, a geometry that's close to the anatomical representation of your left ventricle. Okay? And what we did was we made a mold and cast flexible walled physical models using silicone material. Okay? And the anatomical shape is represented closely at one particular face of your heart, peak systole, peak of the pumping state of the heart. Okay? And then what we did was my favorite thing, gather a bunch of PVC pipes, nuts, bolts, hose clamps, and put it into a flow circuit. Okay? This flow circuit is nowhere close to the complexity of your real organ, right? But here's what it does. So you have a programmable piston pump that basically goes back and forth. This whole thing is filled with water glycerin in a box. And inside the box is this artificial heart. Okay? So as this is pushing and pulling, the vacuum or the positive pressure is going to create suction and pumping. And so as it does that, we have prosthetic heart valves that create flow only through one way, similar to your natural heart valves. So it prevents flow going the wrong way. And then to simulate elasticity in blood vessels, we have a lumped compliance chamber. So this is very similar to a shock absorber. Part of it is air, part of it is incompressible water glycerin fluid. So depending on the air, the ratio of this, you can actually create fluctuations in the pressure in the system. And then we have a resistance that's basically like a choke. So it can control how much flow goes in and out of the system. So it can regulate how much blood, in quotes, your heart's putting on, cardiac output. Okay? This is how it looks. So it's an idealized representation. Your heart moves in a much more complicated manner. So we're not there yet. But what we have is something that's clear, I can see through it, I can put particles, beads, whatever in there, and study how flow moves inside. And all of a sudden, I can play tricks on the material properties of this to try and get to the questions of, hey, what happens if your heart is stiff? Does it create a problem? And what if it's stiff 3 times stiffer? What if it's 2 times stiffer? When is it going to be a problem? How is it going to be a problem, right? So the hemodynamics that we get, in short, the blood flow patterns resemble what we're supposed to have in normal humans. Normal humans fill their heart in basically two distinct portions. One where the ventricle actively suctions and relaxes and accepts blood. So that's the early relaxation or E wave. And then there's a period of almost quiet, nothing's going on. And then your left atrium does a little pulse, it gives a atrial kick. So we've been able to recover that in our simulation. Okay? The aortic pressure we can recover to your normal values if you want 120/80 millimeter mercury. So we're able to get bulk blood flow patterns to be similar. Okay? And we're able to do, since it's transparent, it's optically accessible, we can do qualitative particle flow visualization, or we can do particle image velocimetry or PIV, where we use a powerful laser beam and then convert it into a sheet, and the sheet cuts at a piece of the heart model, and then we use cameras to look at how little tracer particles inside are moving. And eventually we can get quantitative velocity maps on the entire heart from them, okay? So what did we do was, here's the goal of our experiment, is to take MRI measurements on this. By the way, this was made with brass, non-ferromagnetic materials, so that we can actually put it in an MR scanner, okay? Going to the scanner and testing whether it was MRI compatible was one of the most scariest days of my life. Because before I went in, they told me that the price tag on this was pretty serious. And I said, oh, okay. There's a little part that created some interference. Luckily, it didn't hit and break anything. Okay? Just got lucky there. So, what we wanted to do was MRI typically in patients is very high resolution in space. We get very beautiful, high spatially resolved images, but time resolution is usually not so great. Okay? Usually it's about 20 different pictures for one heartbeat. Okay? Depending on the type of heart motion you have, the type of disorder you have, that may or may not be enough to reconstruct and give an accurate representation of what your heart is doing. So what we decided to do was just put markers on the wall of the heart and do a stereo imaging with high-speed cameras at a high frame rate and be able to reconstruct the motion from that. Here's the way we did our CMR scans on the model. So we actually acquired a whole bunch of cross-sectional views. Okay? So you'll see raw images in a second. So we took many different planes across the heart, 15 planes, and each slice was about 6 millimeters thick. And we acquired 128 phases a cycle. If you remember, I said it's about 20 phases a cycle. We acquired quite a bit of high resolution here, so we haven't dialed it down yet to see when it would create a very big mismatch to our lab. We wanted to start by saying, I'm going to crank this up to see when it's going to match. And this is pretty much as good as we could get without sacrificing the spatial resolution. And then we also did flow using MRI, so phase contrast sequence, where we just looked at a central plane and we did PIV on the same plane. So here's different pictures of the MRI, and so what you see is the border of the wall moving and different parts of the cardiac cycle. Different systole for pumping, diastole for filling. Okay? And so now what we did was we used MATLAB algorithms to track this border, right, to get the volume of the heart in time. Meanwhile, in stereophotogrammetry, what we did was we took these two images and then we put a MATLAB code that does direct linear transformation in very small little areas, localized, and then we actually constructed how the heart, those points are moving in time, right? And then we mirrored it across the center line. We didn't make an assumption that it's center line symmetric. and it's mostly true with our physical model. So here's a representation of one particular time instance of the point cloud, okay? So the MRI, if you remember, gives you volume by tracking the borders. And I can do the same thing here. The internal volume can be calculated. And now I can put them both side by side and see how good they are. So the first thing we did was calculate LV, left vertical volume, and compared it between stereo photogrammetry and the flow probes. I said there's two flow probes. I don't know if I said it actually, but there's two flow probes that we use that we couldn't put in the MRI machine. They gather flow rates, volume per unit time, at more than a kilohertz. So they're very high resolution data. So we put them both together and we looked at them side by side, quantified the difference in volume between stereo photogrammetry and flow probes. And it turns out the average discrepancy was about 5.9%, give or take. Okay? So that's where we're at in terms of how good our stereo photogrammetry reconstruction is. Can this be improved? Perhaps. How? Maybe I can record more images, right? Or I can only do pieces of the heart. I only do little segments of the heart instead of trying to image the whole heart. More time consuming, but maybe I can lower this number down. This is where we're at right now. The next thing we did was we looked at the volume from MRI and compared with the stereo photogrammetry, and then we calculated the normalized volume. And it actually was pretty good in terms of matching together, which was about 5.5% on average. So what this tells us is, under this resolution of 128 phases a cycle with 6 millimeter thickness, 15 slices across the heart, the volume from MRI measurement actually is close to what two other methods with higher time resolution independently calculated. So that's kind of a very new comparison. Nobody done this in the left heart before. And then in terms of MRI-based flow patterns, here's early filling, mid-filling. You see swirling of the flow around the heart model. And with particle visual osmometry in the lab, we got qualitative agreement. And more or less, the peak values are about the same. Okay? So there was a motion, the wall motion. This is the flow. So basically, the kind of the where we kind of wrap this up is that we were able to validate a particular method of CMR reconstruction in MATLAB. Obviously, now we can start asking questions like, hey, I have a Siemens scanner. I'm a cardiologist, and this is what my technicians use to reconstruct in the Siemens scanner. Is that good? So I don't know, but I can tell you. Right? The next thing is we're able to provide the medical imaging, CMR-based wall motion and flow for validation of computational models. So this is a test, a sort of facility for that. And the hope is that we can start asking questions about how good the resolution needs to be for different metrics of pumping, of heart function. In other words, when can I say I do this MRI scan at this resolution that I will get something that's accurate? Okay. So moving on. So that was a kind of a facility and one particular example of an application. The next thing is more along the lines of